Hello everyone and welcome to my self-learning presentation on the fundamental of quantum computing and its exciting applications. In this video, we will take a glimpse into the revolutionary world of quantum computing. We will start by understanding the core principle that power these fascinating machines. More importantly, we will explore some of the real-world applications where quantum computing promises to make significant impacts. Here's the roadmap of what we will be covering in this presentation. We will begin by contrasting classical and quantum computing, then delve into the fundamental quantum concept of superpositions and entanglement. We will briefly touch upon quantum gates before discussing the current landscape and future outlook of these exciting fields. Following that, we will explore applications in artificial intelligence, securities, scientific discovery. Finally, we will wrap up with the briefly conclusions. At the heart of the difference between classical and quantum computing lie on the fundamental units of information. Classical computers use bits, which are like light switch. They can be either on representing 1 or off representing 0 at any given time. Quantum computers, however, utilize qubits. What's fascinating about qubit is their ability to exist in a state called superpositions. Imagine our light switch not just being on or off, but somewhere in between, representing both 0 and 1 at the same time. This ability to hold multiple states simultaneously is what gives quantum computers their potential power. So let's dive deeper into superpositions. Think of a spinning coin. While it's spinning, it neither head nor tails definitively. It's in combinations of both possibilities. Similarly, a qubit can exist in a probabilistic combinations of the 0 and 1 state. It's only when we measure or observe the qubit that is corrupt into a definite state, either 0 or 1. This both at once nature allow quantum computers to explore many possibilities in parallels. And for another crucial quantum computing phenomenon is entanglement. When two or more qubits become entangled, they become intrinsically linked. Their phases are intertwined in such a way that measuring the states of one entangled qubit instantaneously tell you the states of the other, no matter how far apart they are. Einstein famously called this spooky action as a distance. Entanglement allows for powerful correlations and computations that are impossible with classical bits. And next is about quantum gates. Just like classical computer use logic gates like and or not to manipulate bits. Quantum computer use quantum gates to manipulate qubits. These gates are the fundamental building blocks of quantum circuit. They perform operations on the quantum states of qubit. For example, the Hadamard gates can put a qubit into superpositions, while Pauli gates perform rotations of the qubit state. Before we dive into specific applications, so let's take a moment to understand the current landscape and future outlook of quantum computing. Now we are currently in what often referred to as the NISQ era, which stands for Noisy Intermediate Scale Quantums. This means that while we have working quantum computers, they have a limited number of qubits, and these qubits are still prone to errors. Despite these limitations, they have been significant advancements in the underlying hardware, with various promising qubit technologies being explored, such as superconducting circuit, trapped ion, and photonic. Globally, there is a surge in research and development in both academic institutions and private companies. Importantly, cloud-based platforms are making quantum computing resource more accessible to researchers and developers. So let's looking ahead to the long-term expectations is the development of fault-tolerant quantum computers. These machines will have errors corrections capabilities, allowing them to perform complex calculations reliably. This could lead to quantum advantage. In specific computational tasks, where quantum computers can outperform even the most powerful classical supercomputers. We also anticipate the development of new quantum algorithms and the growth of a robust software ecosystem to harness this power. Ultimately, interdisciplinary collaborations between physicists, computer scientists, engineers, and domain experts will be crucial in unlocking the full potentials of quantum computing. And now let's move to the exciting part, the real-world applications of quantum computing. While the technology is still in its early stage, it promises to unleash immense potentials and revolutionize various industries, tackling problems that are currently beyond the reach of even the most powerful supercomputers. One of the most promising areas for quantum computing is in artificial intelligence. Quantum algorithms have the potential to significantly accelerate and enhance machine learning. This includes developing faster and more efficient algorithms for training complex AI models. Imagine being able to train AI for tasks like image recognitions or natural language processing in a fraction of the time it takes today. Furthermore, quantum computer could excel at identifying subtle and complex patterns in vast amounts of data, leading to breakthrough in areas like data discovery and financial modeling. They can also tackle complex optimization problems such as optimizing logistics for transportation networks or allocate resources with unprecedented efficiency. For instance, in machine learning, quantum algorithms have the potential to significantly speed up the training process for complex neural networks. This could lead to faster development of more sophisticated AI model capable of identifying subtle and intricate patterns in massive data, which is crucial in fields like data discovery and financial modeling. And next, in the realm of security, quantum computing presents a fascinating duality. On one hand, the power of quantum computer, particularly algorithms like Shor algorithm, could potentially break many of widely used public key encryption methods that secure our online communications and transactions today. This is significant concern for cybersecurity. However, this very threat has spurred intense research into developing post-quantum cryptography, new encryption techniques that are mathematically designed to be resistant to attack from quantum computers. And furthermore, quantum mechanics itself offers promising solutions like quantum key distributions, a method of transmitting encryption key with a level of security based on the fundamental law of physics. For applications in science and discovery, quantum computing has the potential to revolutionize scientific explorations across various disciplines. One key area in molecular simulations, accurately simulating the behavior of molecule is crucial for designing new and effective drugs, as well as for developing novel material with specific properties. Classical computers often struggle with the sheer complexity of their simulations, but quantum computers, with their ability to handle vast amounts of quantum information, could provide the necessary computational power to model molecular interactions with unprecedented accuracies. The capability extends to materials science, where we could design and discover new material with design characteristics, such as more efficient energy storage or novel electronic properties. Furthermore, in quantum chemistry, quantum computer could allow us to understand and predict chemical reactions at fundamental levels, leading to breakthrough in various industrial processes. Um, Quantum computing holds immense promise for revolutionizing scientific explorations. For example, in dust discovery, accurately simulating the behavior of molecules is crucial for designing new and effective pharmaceutical And classical computers struggle with the complexity of this simulation, but quantum computer could provide the necessary computational power to model molecule interaction with unprecedented accuracy. Similarly, in material science, quantum computer could aid in the design and discovery of novel material with specific properties like new superconductor or more effective battery materials. This extends to the field of quantum chemistry, where understanding and predicting chemical reaction at the fundamental level could lead to breakthrough in various industries. And in conclusion, quantum computing in a rapidly evolving field with the potential to bring about transformative change across numerous industries, from building the capability of artificial intelligence and revolutionizing cybersecurity to accelerating scientific discovery in areas like dust development and material science. The applications are vast and exciting. While the technology is still in its early stage, continuous research and development are crucial for unlocking its full capabilities and realizing the quantum futures. And finally, here's the reference for the material I consumed while preparing these presentations. So if you have any questions, please leave it below in the comment sections. And thank you for your watching and see you. Thank you.